module number 5, joined by Gary Wish, who's a vice president with DeLong's Inc., which is a steel fabrication company. He's going to be presenting on a steel fabricator's perspective, fabrication and constructability.
Thank you. All right, well, thanks to each of you, and a thank you to Dr. Azizi and the folks at Florida International University for inviting me to speak with you about SDCL from a fabricator's viewpoint. My name is Gary Wish, and I've spent my entire career, 43 years to date, in the steel fabricating business. I'm employed in the engineering department at DeLong's, formerly as a vice president and now as kind of a consultant and advisor to our engineering and business development. But there are about 80 firms like us in the country that actively fabricate steel bridges, and we're kind of middle of the pack. The company has been in the bridge business since long before I was born, since the very beginnings of the interstate highway system. So we talked through the day about what SDCL bridges are, and of course I have a unique perspective. I am not an owner, nor a designer, nor a contractor, but just a material supplier, a fabricator. And to explain from our viewpoint what the SDCL bridges are, I feel like it's necessary to spend a fair amount of time talking about what they are not. And so let me take just a few minutes to do that. First of all, in the case of farm, they are not plate girders. Now, depending if the spans were larger, the designer could have called for plate girders, but these spans were all of such a length that wide flange beams would work. I believe it's been noted before that the largest beams used in farm were W24s, and the heaviest beams were around 150 or so pounds per foot. So what that meant for us is that many of the operations, such as cutting flange plates, were not necessary. This is one of 2 plate burning tables that we have, and multiple heads can cut out multiple torches at a single time, but we were able to completely bypass this operation. There are no shop welded flange splices. This is a really expensive operation. It can be used for one of 2 reasons. One is when the engineer wishes to change the size of the flange within the length of a particular shipping piece, and the other is that if the piece were too long, beyond the maximum of what the mills can roll and ship to us, then we'd have to shop splice 2 pieces together that were of the same size. But the joint preparation, the welding itself, and the inspection of this weld are all time consuming and costly. We don't need to cut a web to a cambered shape. This is our other burn table, the one that we usually process the web plates on. And once again, by using rolled beams instead of built-up plate girders, we were able to bypass this operation also. This was the biggest operation that we were able to skip. Because the beam comes from the mill already in the wide flange or I-beam shape, there's no flange to web weld. The machine that you see here is a submerged arc welding machine. It's really kind of what makes bridge fabricators different than from other fabricators. By not having to go through this operation on farms specifically, more firms can bid on the job and prices can be more competitive. I want to explain a little bit about what all is going on here so that you kind of get an understanding of what we didn't need to do. This is a preheat torch. It runs ahead of the welding machine. There's 2, it's a twin head machine, an AC lead and a DC trailing wire. And so there's actually 4 spools of wire feeding this machine, an AC lead and trail wire on the top flange and a lead and trail wire on the bottom flange. There also is a preheat torch down here. You just can't see it because the flange is in the way. So with this machine, we can get a 3/8 fillet weld, top and bottom in one pass. This is actually the second side being welded. When we did the first side, we had it over in this bay where these clamps squeeze the flanges to the webs. Then we pull it out of the jig where it gets squeezed, and we weld the back side. And there again, all of this was omitted on each of the 25 SDCL farm structures. The other big thing, Jason just got finished talking about how bolted splices were expensive and time consuming in the field. Well, I'm here to tell you that the same thing is true in the fabrication shop. This picture on the left is a bolted splice that we haven't yet taken apart. It's clamped together. It's actually got drift pins in it on both ends. The pins, we drill the 4 pilot holes first, put in the pins. It holds everything in place, and we use a CNC drill to drill the rest of the plate. We match mark all of these so that the plates, so that we're assured that everything will fit in the field, because we have it all pre-assembled here. If the erector gets it put back exactly as we have it here, we're confident that all of the holes will line up. The right-hand side here is our drilling area. This bay is where all of the drilling takes place. Also in this bay, we do our final dimensional checks. We string a wire from end to end. You can see that wire hanging right there. And we measure off of that wire. That ends up checking our vertical geometry. With the girder laid down, we're measuring horizontally from the wire to the bottom flange. And if we had a curved bridge, then the ends would be up in the air, and we would use a surveyor's level to check what eventually becomes the horizontal geometry. With SDCL, a total assembly is not required. Now, this doesn't happen on our run-of-the-mill day-to-day bridges, but depending on geometry and contract requirements, some bridges have to be fully assembled, as shown in this picture here. Sometimes we do this due to contract requirements, but sometimes we make an internal decision based upon the complexity of the job. We know that there are high costs per day for lane closures. Sometimes the costs get down to per hour or per 5-minute increment. And when those costs get really high, to assure ourselves and our customer or erector that everything is going to fit just fine, we put it all together in the shop. We invite them to come in and look at it. We take all kinds of pictures and video so that we can have confidence a complicated geometry is still going to fit together and work out just fine. So on these, the foam bridges were all painted. And I'll get into a little bit more detail about this later. But at the very beginning in the design phase, when we were first being, or before the design phase really, when we were being contacted by contractors, we evaluated the option to go with weathering steel, painted steel, or even some other types of coating. And I wanted to show this just so you'd understand a little bit about the difficulty. This is a plate girder that's coming out of our automated blast cleaner. We run it through there even on an unpainted weathering bridge, just so that it begins to get a uniform patina so that it will weather evenly. But we can run it through really quickly and just with a single pass. If it's going to be painted, we've got to reach an SP10 near white blast as opposed to an SP6 commercial blast. And so we run it through once, we flip it upside down, we run it through again, we run it a lot slower, we make sure we get into all the nooks and crannies in there to get it clean enough to hold paint. So as I said, the bridges, if they're weathering, they don't need to be coated, but if you're going to use a grade 50 that needs a corrosion protection system, you still have some options. They can be painted, galvanized, or metallized. This particular picture was taken at a subcontractor who does metallizing work for us. Generally speaking, the metallizing is only required, you would only go that route if your pieces were too long to fit in a galvanizing tank. And as one of the earlier speakers noted, the tanks are at least 50 feet long now, and in some cases longer. And I'll show a picture here in a little bit about how you can even overcome that limitation to some degree. I happened to take a picture in our yard one day this summer. In general, about half the bridges that we fabricate are uncoated. And I took this shot from the yard, and in this storage area, this is our finished product storage, we didn't have a single coated girder in here. These pieces aren't waiting to go into our paint building. They're finished and ready to ship. So it's not to be used in every case, but there are places where it can provide a good, inexpensive means of protecting the bridge, and that's to use a weathering grade. So what do we have? We talked some about what we don't have. Let's talk about what we do have. All of these beams are rolled beams. We purchased from 2 domestic suppliers. This picture was taken from a mill at Nucor Yamato in Northeast Arkansas, showing the beams going through the roller. Shout out to Shane Vernon at Nucor Yamato for sharing this with me. what happens here, the steel begins to cool and it's in a square or rectangular shape, but it's still somewhere between 2,000 and 3,000 degrees. So it's fairly malleable. It goes through these rollers, and by the time it's finished and comes to us, it's reached the wide flange, be it a W18 or W24 or whatever it is that we needed to order for these bridges. So the roll beams are a lot simpler to fabricate than the plate girders, and we're going to kind of try to go through a step-by-step here that shows what it took for us to do several of these farm bridges. We have a beam line that will drill and scribe and cut beam all the way up. I think this particular beam line will do up to a W36. There's some that'll do even larger than that. I know the mills will roll up to and including a W44. We regularly fabricate up to a W36, and we've done some W40s. I don't know if we've ever done anything quite as heavy as a 44. But so in a typical continuous design, we check bearing to bearing lengths during our splice drilling operations and cut the beams or plate girders to length with a torch when the splices are drilled. But this is a bandsaw, and it's part of our drill line. So when the beams come through here, we're going to get the holes for the rebar drilled, or if they want slots to allow for expansion and contraction, we can burn those with either oxyacetylene or we can use plasma. And then it comes to this bandsaw and it's cut to length. It also, the beam line will put a scribe mark on the web where the stiffener is to go. And it will also put a dimple in the top flange where each of the shear studs go. And we'll talk about that a little bit more further down the line also. If the design plans call for it, and some of these spans were long enough that it was required, and on others it was not. But we can camber. We have two means to introduce camber into these roll beams. In one of our 3 fabrication facilities, we have a cold cambering machine that actually will grip the ends and apply force as needed, intermediate section of the flange to induce, to get it beyond its plastic region, to get it beyond its elastic region into the plastic region and apply camber that won't all come out when the force is released. Some states allow that and some don't. And if they don't, we apply heat. The beam in the sketch is in a finished position. We actually induce the camber. We induce the heat when it's upside down. Top flange is on the bottom flange is on the top, and that way gravity works for us. We apply heat with a torch in the areas that are colored in there, starting at the flange and then moving into the web. Each of the technicians is going to have a heat stick with him. Specs usually require or don't allow a temperature in excess of somewhere between 1050 and 1150. And so we have multiple heat sticks that will melt when the steel reaches whatever the prescribed temperature is, and that's how they know where they can be safe and where they can't. We try to set a bunch of these up in a row so that as the technician moves from beam 1 to 2 to 3 to 4 and so on, beam number 1 is cooling, and by the time he gets done with his row, he comes back and beam 1 is cooled. He strings a wire from end to end. He checks his camber, checks to see if it's within the tolerance, and if it is, that's great. And if not, he'll make adjustments at some in-between locations. These show cambered beams in the field. You would think when you look at this that there's no way you could get a good riding surface off of beams that look like this, but the camber is added for one of 2 reasons, possibly both. One is to account for dead load deflection, and one is to account for vertical curve. This particular bridge was on a straight grade, so the camber was only for dead load deflection, and that means that when the slab is poured, it's going to flatten out, and you're going to have a good straight grade and a decent riding surface. We're down to where one of the more complicated things on the SDCL is installing the diaphragm connection plate. So we have several options. We can use submerged arc, we can use flux core, or we can use shielded metal arc, SMAW, also known as stick welding. Some owners don't want us to use flux core on stiffeners. That on beams of this size, W12s to W24s, flux core would have been our preference. When you get into deeper beams, submerged arc is preferred, at least in our shop. But when you're down under 30 inches, the time it takes to set up the welder to straddle the stiffener and weld both sides of it at the same time, it just doesn't pan out. The setup time isn't worth the time savings when the actual welding is being done. So we prefer flux core for stiffeners of this size. We can put these in at 90 degrees. So on a square bridge is certainly what you would do. On a skewed bridge, the designer has two options. We can put them in at 90 degrees and then stagger the diaphragms across the width of the bridge, or we can put these in at a skew and then the diaphragm is also put in at a skew so that it ends up being parallel to the piers in the abutment. The next thing we do is install the end plates. This particular bridge was not on the farm project. It was on the Northwest Missouri bundle that came a little bit later. If the folks at Wilson, Jason spoke earlier, if they had not used this end plate and gone with a traditional bearing stiffener, we would have had to, first of all, we'd have to clip the top and bottom to fit around the beam fillet. We would probably have had to have done a full penetration groove weld at the stiffener to the bottom flange, and then that would have required ultrasonic testing, which we don't do in-house. We would have had to subcontract that out. And on this particular design, a full-length weld wasn't required. We were able to stop some inches short of the top and bottom. I know on farm all of the end plate to web welds were designed to be full length. Then we go to the end blocks. They are tacked and then they're welded. Once again, we can use flux core or SMAW stick welding. Flux core is faster. We've got more guys qualified with that. It seems to be a little bit easier, so that's preferred. I believe Jason mentioned that they used a square end block on all of their designs, 3 inches by 3 inches, and the length of the block matched the width of the flange or the width of the end plate. We prefer those square blocks. We have done some, I think altogether we fabricated 50 some of these SDCLs now, and we've done some with some rectangular edge blocks as opposed to square. And there's way too many places where things can go wrong in a fabrication process. And if you've got a 3 by 3.5 end block, there's some likelihood that the dimensions are going to be switched and it's not going to end up being installed the way the designer intended. So the automated beam line that we showed earlier on puts a dimple in the top flange where each of these studs go. So the operator here doesn't need to string a tape measure from end to end. He doesn't need a chalk line to lay out where all these shear studs go. There's a little dimple in the top flange at every one of these locations. So all he has to do is set the stud in place, put his stud gun over it, pull the trigger, it melts the bottom of the stud, bonds it to the top flange, and he's done. Now, we have a QC check on this that we do every day. We actually do it on every beam. He's going to shoot on the first 2 studs, and they were to the left of the picture. I should have showed them. Then he stops. He'll take a pipe and set it over the top and bend the stud over. And if the weld doesn't break, then he knows that his machine is set up properly and he's good to go. I'm going to take a few minutes and talk about coding because it's real interesting how this all came about. When the contractor first approached us, Layman Construction out of California, Missouri, they were interested in the least expensive fabricated price they could get. So we told them that uncoated weathering was going to be the least expensive corrosion protection system. But then he started talking about schedule, and we have a little bit of an issue there with weathering steel. It's not as common, and outside of the bridge business, it's not as common. So to go and buy it, you can't just go to the nearest steel service center. It's unlikely that they're going to have weathering steel in stock. So we have to wait for a mill rolling, and the mill rolling takes place, maybe every 3 months, maybe a little bit more often than that. But if your timing is wrong, you miss a rolling schedule. And then by the time the beams come in, we haven't started fabricating them yet, and the contractor is wanting delivery. So I suggested that they consider galvanized beams. It would be a little bit more expensive, but with galvanizing, we can use a regular A709 grade 50. We can buy them from a service center. We can get them in days instead of weeks or months. And after we got through the first 3 or 4 of these, the shop drawings went really quickly. We were getting them submitted for approval in about a week. So the drawings were coming back at the same time the steel was coming in, and we could meet the contractor's delivery requirement. And as it turns out, at the time, we didn't know this at DeLong's, but Layman Construction did. MoDOT has a point system for how they determined which proposal was the preferred, and they gave points for durability and longevity and low maintenance. And galvanizing helped the contractor engineer team gain enough points that it was one of the factors that helped them win the job. So once we decided on galvanizing, I wanted to show this picture here. It's not an SDCL bridge, but this is a built-up variable depth plate girder, and it's even longer than the beams we did for the farm project. And he's already dipped the end that's on the right-hand side of your screen, and he's just pulling the far side out, and you can see a line across there, and there's a similar one right through there. That's the progressive dip lines that show where the limits of how far they could get piece into the tank. But they got a good a coating that meets all the ASTM A123 thickness requirements. This line and this line are going to remain visible once it gets out in the field for maybe a couple of years, but then it's going to fade out, and you'll never know that it took 2 dips to get this into the tank. A thank you to Alec Novotnik from VNS Galvanizing for providing this picture. I think a picture's worth 1,000 words, and this shows what they can do to coat some of these longer pieces. Everything we fabricated on this project is subject to inspection by the owner. The owner can send in their own staff or a third party. On the farm project, MoDOT had a bridge division inspector in our shop every single day that we were working on the project. Then we sent the steel off to the galvanizing shop, and MoDOT sent somebody from their materials department in the district located nearest the galvanizer. They're taking the galvanized thickness readings here. When they're finished, they give us an inspection release. We send a copy of that with the truck driver, and that way when it gets to the field, while it's being unloaded, the contractor knows that the pieces have met the approval of the owner. With these being in state, we ship most of these farm bridges with our own truck and driver. Roughly half of these structures were small enough size and weight that all of the structural steel for a bridge could fit on one trailer. It says all the beams, all the diaphragms, the bearings, and the hardware. This particular truck was leaving early one morning and going to the first of the farm bridges that we shipped in Macon County, Missouri, about 100 miles north of our plant in Jefferson City. So I'm going to show just a little bit from the field. I know the previous speakers have done that, so I won't dwell on it too long, but I did have the good fortune of getting to see a few of the jobs after we had shipped them and when they were being erected. This is what the end blocks look like in the field. This is at an intermediate bent. And as Jason mentioned before, the beams are set on elastomeric bearing pads. I believe we were using the 5/8 with a single shim in them here and a 1/2-inch thick plane pad at the abutment. On the next SDCL project that we did in Northwest Missouri, there were no bearings at the abutments. They welded the end directly to the piling. I don't know the reasons why one was one way and one was the other, and I don't know if there's an advantage to one over the other, but we just, as a fabricator, we kind of just do what the designer tells us to do via his design plan. This is a view from a little bit further back of the intermediate vent. I really showed this because I wanted to show the crane pulling out. It's a lightweight rubber-tired crane. They built a small landing pad in the stream for him, and this was taken on the same day that I took the picture of the truck leaving the yard. And the truck got to the job site mid-morning. I got to the job site mid-afternoon, and they already had all 12 beams and all the diaphragms set, and they were pulling the crane out and sending him on his way to the next project. Kudos to Jason and everybody at Wilson. We talked about making SDCL simple, and they really did. These diaphragms are, in this case, they were made out of C12 by 20.7 channel. There's just 3 holes in each end. We ran them through the same beam line that fabricated the beams. It put the 3 holes in each end. Then it goes automated. It goes to the saw, gets cut to length, goes to the galvanizer, and gets put in place. There's nothing complicated about any part of that. This is another view at a bent. This one also was from Northwest Missouri rather than farm. And I don't know Actually, that's not right either. This was on a traditional design bid build that came along later. And the contractor left a gap in there. And I'm not sure if he got some dimensions wrong and needed the gap and was going to fill it with a shim, or if he chose to erect everything this way and later was going to push it all together. But my point is there's more than one way to get things done, and this bridge ended up successful also. Didn't go together quite as quickly as layman's projects did. Still in a day's time, they got all the beams in and all but a couple of the cross frames. Came back and finished it up early the next morning. I want to talk, I know Brian Hartnagel talked about the advantages of bundling, but I want to talk about it just for a second from the fabricator's viewpoint. Had these 25 bridges that became the farm project, the 25 three-span SDCLs, if these would have been let one at a time, we would not have been nearly as interested and probably wouldn't have been nearly as successful. We did not hit our estimated hours on the first bridge, so we didn't come out well on it at all. But we did roughly meet the hours on bridges 2 and 3, and then from bridge 4 on, we kind of got on a roll and had the same crews doing the same kind of work, and we got better as we went along, as I'm sure anybody would. It was just getting over the learning curve. The bundling is catching on in other places too. I was just at an Illinois AGC meeting and learned that they have 31 bundles in the works, totaling 152 bridges and 22 box culverts. I don't have any idea if these are going to be let by the traditional methods or if they'll use a design build as Missouri did on farm. But to us, that doesn't matter. We're just happy to see steel bridges being used. The flexibility of a simple design and multiple bridges in one project has advantages for everyone. For the contractor, if they run into a utility issue or a site work problem or problem with a crew and they're falling behind on one bridge or they can't get to one bridge, with having 25 of them on their books, they can rearrange and it's not too difficult to keep working and not lose time. For the owner, they can use different contracting methods. They can use design build. They can use design bid build. And Missouri is a fan of the fixed price variable scope, but that's just one method of using design build. If, had they decided which bridge, instead of choosing 41 bridges and letting the contractor decide what they could do for X number of dollars, they could have said, we know we need to get these bridges finished, so give us your best price. And so it can be done either way. From the fabricator's standpoint, what we liked about these is they're all small. There were only a handful of beams in the entire project, and there were 300 beams in the project because there's 25 bridges and 12 beams per bridge, so that's 300 bridges. But there were only a few of them that weighed over 3 tons. Well, our smallest shop has a 3-ton crane in it, so we can fabricate these beams on any of our 3 shops. It allowed us a lot of scheduling flexibility. We could meet this contractor's delivery requirements and those of our other customers where we were working on their projects at the same time. We were able to keep all of our people working through the duration of this project, never had to have anybody laid off, never had to have any delays. And that is all I have. I've got my contact information up there. I'm always happy to talk about steel bridges. So if we don't get to your questions here today, shoot me an email and I'll be glad to talk to you about them. And Paul or Kathy, with that, I'll turn it back to you.
Okay. Just have a few questions, but we do have, and some others, I guess we have some. One of the questions came in a little bit before your presentation. It says, were any of the farm bridges heat cambered since web cutting was not utilized? But really, these were small roll beams, and you covered it on your slide 15. I don't know if you want to add anything to that.
Well, the middle span on some of the longer bridges needed to be cambered, and we used cold cambering if it was fabricated at our medium-sized shop, and we used heat cambering if it was done in one of our Jefferson City shops. So we did some of both, yeah.
Okay. How long can you go with a roll beam before you need a bolted splice?
Well, it will depend a little bit on the size of the beam. If the good ratio is the length of the beam to the width of the flange probably shouldn't exceed 85. So if you've got a beam with a 12-inch wide flange a foot wide, then you'll want to go as long as 85 feet, but then after that, you'd have to introduce a splice. You can get some rolled beams with wider than 12-inch flange, but those get pretty expensive. And when you get there, it's time to look at the alternative of going to a plate girder.
Okay. In terms of the risk to cost of construction, what are the most risky variables affecting delay and cost overruns? And has this changed in recent times?
Well, as far as delays, for us, the biggest risk would be material acquisition. So we would recommend that the designer choose sizes that are the most readily available. And both of the domestic rolled shape mills, Nucor Yamato and Steel Dynamics, they post their rolling schedules online. So you can look at it and see which beams are rolled more often and which are not. You could use that to choose a size that meets your design criteria that you know you can acquire.
Okay, I'm going to turn it over to Kathy.
Great, thank you, Paul.